Will Owsley is the district conservationist with the USDA and NRCS in Fort Collins and Greeley. Since graduating from CSU with a degree in soil and craft science in 2012, his focus has been to work with and provide technical and financial assistance to ag producers to promote the profitable, sustainable use and conservation of natural resources on dry and irrigated croplands, rangelands, and forest lands. He works alongside with other conservationists as well as assists the local conservation districts with the USDA Farm Bill programs and activities to achieve these goals. So we welcome Will.
I didn't know you had that.
Yeah, I
you stole it from the last one.
Grant Loan and Grow, yeah.
Cool.
Well, the NRCS helps us out a lot.
So we're going to discuss a lot of different things today. It sounded like quite a few of you are pretty familiar with different irrigation systems. So hopefully this first part we can speed through pretty quickly. I just wanted to talk about some different pros and cons of different systems, some generalities on efficiencies, and then we'll get into the management stuff. So hopefully it's not too dry. If anybody has any questions, feel free to interrupt me at any time, and we'll get right into it. So flood furrow, I hope you caught the dry thing. I'm going to kind of start from least efficient to most efficient. Generally, there's a lot of overlap with all of these systems. I thought I put the percentage at the top here. I may have moved some slides around, and that may be later, but flood furrow, we're in the ballpark of like 35 to 80%. Like it's a huge range, depending on how things are set up. And there's multiple ways. This is a huge broad category. There's multiple ways. I need to stop moving so that they can hear me on the mic. So that they can, depending on how the system is set up as far as delivery as well as application, can change a lot of different things. So, surge with gated pipe or just gated pipe, concrete ditch with checks or earthen cutouts, or what's the word I'm looking for? Siphon tubes. Any and all of those kind of fall into this flood furrow system, as well as the upper mountain hay meadows and things like that. We treat that a little bit differently due to other like delivery factors, but it all kind of fits into that same realm. Here's my percentage. So wild flood, again, water always flows downhill. So we're delivering water to the highest point in the field. The water's applied in small flows at different points of the field, hopefully to get that water to spread through the field. But the important key on this one that differentiates this between the others is there's really, when you're in field, there are no, conveyance structures or little ditches or any way to necessarily control where that water goes other than higher to lower. So it can be challenging, and that's why you see lower percentages here. Though it can be the best use for any given field. It just depends on circumstances and context. We'll probably say that. I know it's been said before my presentation, and I'll probably say it a few more times. Speeding on through furrow irrigation. So individual small open channels or furrows which run through the field to transport water down the slope over the area to be irrigated. Furrows can be adapted to nearly any cropping system, except for where you need to pond water intentionally. Included in something like this, maybe like a basin irrigation system that I didn't include, but that's where you're ponding water intentionally to allow more time for infiltration on that system or within that furrow or area. And that's where you see generally those higher percentages within this furrow category. So advantages, it's very adaptable. You can have you can size streams exactly for your soil intake and your crop needed, and adjust the number of furrows to be irrigated at a given time. Distribution systems generally need very little water pressure. We're just relying on gravity here. The water is not directly applied to plants itself, so the leaves stay dry. That can help with eliminating scalding, pesticide loss from the leaves, as well as several pest and disease and fungal issues that certain sensitive crops can have. And you can have excellent surface drainage. What I mean by that is you can, one of those beneficial uses is to infiltrate salts down below your root zone. You can do that fairly easily with a flood or furrow system that has some that you can't do with some other systems. One of the disadvantages, again, salt. Salt can go from the soil or water supply may concentrate in the ridges. So if you have your furrows up here, your water's in the bottom of the furrows. That salt through matrix potential of the water movement into the tops of those furrows can concentrate salts in certain places. And where are your plants generally planted along those rows? It's at the top of those ridges. So if you have salty soils or a generally saline water supply, that can be an issue to watch out for. Another disadvantage is the lateral spread of water in some soils is not adequate to get that water up to the top of those ridges or the top of those furrows where the water is actually needed, especially for younger plants. Differences in intake opportunity time. I have a picture of that that'll explain a little bit better than words. And depending on how that system is set up and your slopes, soil erosion based from your irrigation system, or we call it irrigation-induced soil erosion, can be a major issue. And then the labor requirements for moving water around are going to be pretty high there. This is a very hands-on system. And so the labor requirements are generally the highest on these systems. A lot of times when we get people wanting to improve an irrigation system from flood or furrow, their main goal is to reduce labor costs. That's not a natural resource that we can necessarily, take points for to address a natural resource concern, but it's always front of mind. So keep that in mind too. You can use furrow with conservation tillage, but trash or residue can be a problem. So you can have these dams created mid-furrow where you don't want them. I mentioned briefly basin irrigation. I don't have a slide for that, but it's basically furrow irrigation-ish, where you set up dams along the way to pond that water intentionally. I've never seen residue pond water where you want it to be, unfortunately. So that can be a problem. Just another one of those labor things, going out with a shovel and clearing through and making sure that your residue is not clogging things up where you don't want it. So this is kind of a slide I wasn't sure how to best describe pictorially how your different soils can influence things. So earlier, let's start with that sandy soil on the left. I mentioned, when you have those young plants and your row where the plant is going to be is on either side of the blue. That's kind of the top of I'm not an artist. That's the top of the furrow. Those sandier soils are going to percolate a lot faster, infiltrate a lot faster. So that water is going to go down a lot further. And it may be hard to get that full irrigation, get that water up to the top of your furrows where it's needed, especially with those seedlings or younger crops. Loamy soils are kind of the middle ground. If we were three bears, that would be the mama bear there. And you're not going to have any serious issues one way or another. Your water is going to percolate at a reasonable rate, and you're also going to be able to get water up to those ridges pretty well. Clay soils are kind of the other way around. You're going to get a lot of water matrix potential. That soil is going to pull that water up to the top of the ridges, but you're not going to get very deep infiltration there. So this was a good picture about that uneven flow rates and variable infiltration rates. So this may be caused by a number of different things, different soil types, micro pockets of different soil types along your field. It could be caused by differences in gates or tube, different tube, not sizes, but height from the ditch to the field. If that's going to be different, you might have a 2-inch siphon tube, but if your height is not equal, if you have a larger drop within that tube, you're going to have more water coming out of that same 2-inch tube. So you see a lot of these micro variances that just makes water difficult to control on a fine scale. Now, if you wanted to, just get water over the field, it works just fine. But be aware of these flow rates. So, a lot of times we'll recommend set your tubes, open your gates, however you're applying to those furrows, but then go back out 30 minutes, an hour, 2 hours later, depending on the size of your field and how much water you're applying, and see what that looks like before it gets to the end of your field. And you can kind of even those things out a little bit before it's too late and you're already at the end of the field. You can't really have a good grasp on how fast that water is flowing. So just a couple pictures. I already mentioned concrete ditch with cutouts are pretty popular. Again, these are on flood on alfalfa. And then a little bit about siphon tubes. These are super popular. How many people have set siphon tubes? It's so much fun. Can you do it and end up dry at the end of it? I can't. Yeah, I think I put more water on myself than the field, but it is fun. So siphon tubes can be plastic or metal. They last forever if you take good care of them. They come in a variety of sizes, and that size is going to determine more or less the flow. But then, as I mentioned earlier, within that size, depending on your drop from your ditch to your field and where that tube is set, the flow rate can change dramatically with just a couple inches difference. The nice thing about this is it's so adaptable. You can set multiple tubes per row if you need to put more water on than what your tube size allows, or you can skip rows or whatever. It's super adaptable throughout the season. And then I had there at the end that the actual flow of the tube does matter a lot. So if you look at charts that show how much, CFS or gallons per minute or whatever a tube is going to provide, one side, a 2-inch tube is going to have a table that's 1,000 rows long because of all those different factors. And then I think I have, so the other thing on siphon tubes is you pretty much you have to have either a very level ditch at the top, or most often you have to have check structures in that ditch to be able to raise the water up to a level where where you're not pulling in air into your siphon tubes. Sediment in the ditch can become a problem, and that's both in the ditch and in the field. And then earthen ditches are going to require more frequent burning and taking care of that undesirable vegetation and just general cleaning. Siphon tubes can easily get plugged up, and so maintenance of the ditch is pretty darn important on those. Gated pipe, just another method to move that water from the ditch or from the top of the field into the field. Once it's in the field, everything's pretty much the same. Again, can be plastic or aluminum. Can be single-sided or double-sided. You can have gates on both sides of your tube if you run it through the middle of the field and you're kind of at a crest. The gates are usually on 30-inch centers, and they're very adaptable too. You can't put new gates in necessarily, but you can open and close gates as needed. And then again, sediment and trash, residue, if it's not in the field, I call it trash, can be very problematic. So you want to keep your velocities fairly high. I think the minimum recommendation is technically 1.5 feet per second, but just for safety, I kind of put a little bit of a factor in there. 2 feet per second is probably going to be enough to keep your gated pipe pretty clear of sediment. I like and I don't like this picture because it does do a good job of showing the erosion that can happen right at those gates, and that can be very problematic. So there's these erosion socks that can kind of solve that problem. It just clips onto your gated pipe, and then it's just literally like a nylon sock type of a thing, pretty thick, to slow that water down, spread it out before it actually hits your field, and it gets rid of that energy that the water has, or most of that energy that the water has that would be erosive at the top of your field. Moving on to sprinklers, this one has been more and more popular in the last several years, and I'll talk about why here in a minute. But basically, traveling system consists of a large impact type sprinkler. We call it a big gun, and then it's on a reel that will slowly bring that big gun towards the reel, and so that's the traveling part of it, to move it along those traveling lanes. The reason these are becoming more and more popular is because they're very well adapted for irregular shaped fields. Over the last 20 years, a lot of people have put on pivots and stuff like that on their square fields and where they fit. And now a lot of the folks that come to us for irrigation system improvements are on irregular shaped fields because the nice, pretty square ones have already been done. It is capable of high uniformity for water application, but it's very important on these to make sure that your operation and maintenance is up to par in order to get that high uniformity. So this picture is a little bit deceiving, and I'll explain why, but let's get through the text at least first. So that sprinkler, that cart can be moved generally pretty easily, a small ATV or an ATV or a small tractor. Some of them are even small enough to move by hand, though I wouldn't necessarily recommend that, but I'm a lazy government employee. So generally it's one sprinkler is operated on a lateral. If you have multiple sprinklers on there, you get weird things with your pressures, and these are very sensitive to pressure variation. So we just recommend one sprinkler gun per lateral. And then the operation, the nice thing about these is the operating pressures you've got a wide range of operating pressures that you can operate in. 50 to 120 PSI I put here. Same thing with flow rates, 50 to 1000 GPM is pretty common. Everything will need to be designed within the parameters for your field and your water delivery, but they are very flexible and can be designed. They're also easy to change nozzles and things like that. So if you need to move it and cover a few different fields and have a few different types or water delivery or water requirements for your crop, it's easy to change those nozzles. Again, the application can be highly uniform, but they're greatly affected by wind speed. Anything over about 4 miles an hour, you're going to start seeing some differences in your uniformity. 4 miles an hour is not much around here. The larger droplet size, which can help alleviate some of the issues with wind, can do some damage to crops and cause some erosion. So it's always a balance. What I don't like about this picture, it's a great diagram, but ideally we'd move the active one for the folks online, the second from the right line there, tram line, we would move that over so that you have 50% overlap on those, so that your spray here is actually hitting the tram line on your first run. So that means you're going to lower your GPM a little bit on your sprinkler, or you might run it a little bit faster, but you're basically hitting every area twice. And so you can really increase your uniformity and efficiency that way. And at least with NRCS, that's in our spec. So we have to design this system and put those connections to the main line at a spacing that's 50% that covers your 50% overlap. So if you have a 75-foot throw on your gun, that means your connections to that main line are going to be 75 feet apart. So it adds a little bit to the cost, but it's fairly nominal when you're talking about the whole cost of the project. But it does increase your uniformity by a lot. I don't know how I can speed through center pivots because it doesn't seem like that's going to be super relevant for a lot of you, but there are quite a few different types of center pivots. So, they all kind of have their own individual pros and cons and efficiencies and where they work in certain crops. Generally, it's just like any other sprinkler. It's going to reduce labor needs, but they're also very expensive. So these are kind of the different types of center pivots. I just really want to highlight a couple of them. The spray and impact ones at the bottom are like those old 80s ones that you used to see. You see a lot of in Nebraska still because they don't use them a lot. And so they're still working, but that's where you have your impact gun or nozzle on the actual overhead pipe. And those are pretty highly inefficient. The two that I wanted to point out were the LEPA or low energy precision application. You see a lot of those. I'll just skip to the picture here where you have a whole lot of water coming through through those nozzles at one time. And it can be kind of like a fire hose. It's a lot of water at one time. You really have to make sure that your soil intake rates are high enough to be able for this to work. You also have to have pretty flat fields or you're going to have a lot of runoff within those furrows. And you still kind of have to have furrows and they have to be in a circular pattern because you want to hold that water in the furrow to give it time to infiltrate, just because you're putting on so much water at the same time. The pivot may still be 800 gallons a minute, but you have a lot more water. You have that same amount of water being concentrated in a smaller area. So that's the downside with those. The other one that I had here on that right is that sock again. I think there's a company. Well, I know there's a company called Dragonline, and I don't know how. I haven't seen a lot of those take off real well, but this can be either a sock or like a small drip hose that drags along the soil surface there. It does alleviate those erosion issues, but the big downside with these is you now have something dragging on the ground, and if you need to reverse your sprinkler or you have a wiper a sprinkler that doesn't go all the way around, it's really hard to reverse that without having that drip line essentially get tangled in plants and breaking things off or getting clogged up. I'll kind of skip through some of these others. They're basically the same thing. You just have different nozzle types and different heights of your nozzles. Where it says weight on there, that's generally a pressure regulator. So that evens out the efficiency through that whole pivot as well. But yeah, I'll skip through a lot of these. The mid elevation one is by far the most common, just because it's the most flexible, as far as different crop types and things like that. But again, it's easy to switch out these nozzles if you have different crop needs, but it's not something that you're going to want to do annually, because you're going to have a couple hundred nozzles on those things. Advantages and disadvantages. I don't need to read through each one of these because I do want to get to the better part of the presentation later. But the big one on really all sprinkler systems, not just pivot, is that high initial cost compared to other surface systems. They're sensitive to wind. And then another one that a lot of people don't think about necessarily is the energy requirements tied to pumping costs. If these are all pressurized systems, they're generally going to have at least a booster pump, if not a full-on, 25 to 40 horsepower pump on a pivot. And that gets real expensive real fast as far as power needs go. We're talking multiple thousands of dollars a month is very, very common. Drip irrigation, probably a little bit more relevant to the room here. Supplying water via slow, frequent applications, either onto or into the soil surface, through a network of valves and pipes and tubes and emitters. So it says typical at the top. I stole this picture from Toro. I'm not recommending Toro necessarily. They just had a good diagram. Lots of different layouts that can be achieved through drip systems, and they're all very unique. They're all pretty much highly engineered and specialized systems. So if you're interested in drip, definitely talk to us, but you'll also want to talk to probably a PE to get everything designed properly for your soil intake and your crop needs. Some of these different emitters, stuff like that, are more flexible than others, and we'll get into that right now. So you have your point source emitters. So those are fixed spacing on that drip line, but these are generally above surface, versus the inline integrated drip emitters down below that are generally your subsurface drip irrigation ones. And those look like this picture in the top right. So it's built in to that drip hose. And then within that black part that's on the hose, it's basically got a little maze that water goes through. And that catches any sediment that could get through your filters and into your hose. And it's also part of the pressure compensation. So if you have, if your hose is pressure regulated to 10 PSI, but you're putting 20 PSI at the bottom of the field because you've got gravity working on that water as well, the water coming out of that is still going to come out at a rate that is equivalent to 10 PSI. So that helps even things out quite a lot. Again, increase your distribution uniformity. Again, those ones are generally pressure compensating. I do have on here that they're not always, but most of the ones I've seen in the last 10 years are pretty much always pressure compensating. The next one is those online button emitters. Those are installed manually, which is a positive and a negative. It means you can put an emitter wherever you want it, and you're not limited to the spacing of emitters that the manufacturer decides that you need. But there is that kind of manual requirement to actually install those emitters. They can also be pulled out and plugged. So it is very flexible from year to year. So those are useful for variable plant spacing or any kind of retrofit or anything like that. The micro sprayers, bubblers, those are kind of a ubiquitous term in my research, I guess. Some people will call things bubblers that might fit into another manufacturer's definition of microspray, but they're all kind of the same thing. The whole goal here is to emit water in a small spray pattern or drip pattern onto the soil or into the root zone. And then you have your porous soaker hose that you can basically buy at Home Depot. Not super efficient, no pressure compensation or anything like that. You're going to have higher pressure. Generally, you're going to have higher pressure at the inlet. And then the interior of that hose is super rough, so you're going to have a lot of losses within that hose, and you're going to have lower pressure at the end, and that's going to cause pretty variable irrigation rates along that length of that hose. Drip also has a lot of advantages. You can apply fertilizer and nutrients directly into your irrigation water. Very high application efficiency. No field leveling required. Generally, again, most of these are pressure compensating, so they can take advantage of or not be affected by changes in elevation in your field. And you can keep that root zone soil water content at a fairly constant level as long as you have available water, which I know doesn't really fit into today's conversation. Again, highly uniform, very low labor, but it's expensive. That's definitely number one on here. 2,000 to 5,000 plus. Generally, the smaller the field for drip, it gets really expensive on a per acre basis pretty fast, because you still have to pay for the pumps and the filters and all that stuff, and that cost isn't spread out over a whole lot of acres. So on a per acre, I wouldn't necessarily focus on the per acre costs too much. Just generally know that the smaller the field, the more it's going to cost per acre. And we can talk more about some of the advantages and disadvantages later when we go out and see it in person. I think that would be a little bit better. So I kind of mentioned all of these things on all of these slides, but there's a lot of different considerations when talking about which system fits for me. And a lot of it is down to cost, installation, maintenance, labor, all that kind of stuff. And then water supply stability kind of a thing. The infiltration rates and all that kind of thing, those can generally be designed around just about any system, but it's still important to think about and consider so that system is designed for your specific needs. And then I also put this in here. So we're going to transition into some irrigation water management stuff. I'm going to call it IWM. I apologize. Again, government, I like acronyms. That book on the right, I brought several copies. Jess has one up there. There's a few more copies on the table, and if those run low, I've got some extras. It's a really cool book, but I will say, if you're just going to take it and throw it in a drawer, please don't take one, because they're kind of hard for me to get. But if you are going to use it, please take it, because they're super handy. The back side of it, it's kind of weird. Half the book is printed upside down, because the back side is more about maintenance and equipment management, stuff like that. And then the front side that I have here is all about water management. So a lot of the numbers that I pulled as far as different efficiency rates and stuff like that, and a lot of the numbers I'm about to pull here later come either directly out of that book, or the book will reference them as well. So you don't have to take a whole lot of notes here. So the whole point of water management is to manage the water in your soil within that root zone, right? So each crop is going to be a little bit different, have different rooting depths. In general, this is kind of how we like to think about it. The highest amount of water extracted from the soil is going to come in that top quarter, and then 30%, 20%, 10%. So most of that water is not being pulled from the bottom quarter of those roots. And that's important to take note of. Once you get into that bottom quarter, if you have higher water content down there, but not at the top, that plant is not going to be able to pull very much out of that bottom quarter. And so you're going to have that deep percolation, which can be a net positive. We'll talk about that a little bit. What I wanted to highlight here is different water holding capacities on different soil textures. It's generally thought of as your lighter, sandier soils have lower water holding capacity, and that's absolutely true. But it's not linear. So as you get into your clays, which I think are, that 1.8 to 1.9, clay is going to be your heaviest soil. It will hold more water, but as far as available water that your plant can actually access, it's a little bit lower than your loams and your silt loams and your silty clay loams. Because that clay is holding onto the water so tightly that the plant can't drink from that straw hard enough to pull the water away from the soil. So you kind of have a little bit of a inverted U curve on your available water. And I've said available water a couple of times. Let's get into some water terminology. We'll go through this pretty quick because it's fairly simple. Field capacity is the amount of water left in your soil if you have it completely saturated and that water is allowed to drain for 24 hours. At that 24-hour mark, generally you're at field capacity. So that's that line there. Permanent wilting point is going to be this bottom line. You still have water in the soil. It's not oven dry, but the plant can't access that water. So your available water is between permanent wilting point and field capacity. And then your management allowed depletion is going to be somewhere here in the middle. And we'll talk about how that's set here in a little bit. But for your local decision making and circumstances, it's important to be able to know what is your available water holding capacity. So you can look up your soils on Web Soil Survey or Soil Web or anything like that. What I've done here is broken it out by layer, which Web Soil Survey and Soil Web, which is an app if you're not familiar with it. If you're standing in the field, you can just say, what's my soil? And you can look at each layer. It'll give you the water holding capacity for each layer. So in general, what I did here, we're on an alt-van loam, but that sounds a lot more consistent than it actually is. So the top 12 inches of that are a loam texture. Then inches 12 through 23 are clay loams. So they're going to have a different available water holding capacity than your loams. And then it goes back into a loam. So you take the thickness of your layer, multiply it by your available water content, which is inch per inch or centimeter per centimeter. It's a unitless measurement. And then multiply each of those across and you get your total available water capacity within that layer. And then you add them up at the bottom. So I just did 36 inches because I was in a hurry to make this. And I didn't want to go down to 4 or 5 feet. But for that 3-foot effective root depth, in this case, this soil can hold 6.2 inches of water that is available to the plant. Again, it can hold more water than that, but the lower section of that is not available, so we don't count it. Okay, what about my soil? And I don't like math. So we have common methods, and Ian will talk about a lot of those later, so I don't want to get into different instruments too much today, but feel and appearance of soils. So you can go out there, touch the soil, grab it. There are a lot of guides online, and I should have brought some handouts, but I didn't, for how to determine what your water capacity is of your soil just based on feeling it. That'll give you a pretty rough guess, but it's better than nothing. Various field instruments that Ian will get into later, and then bookkeeping methods. You can look at your daily consumptive use versus your precip and irrigation and just treat it like a checking account with inflows and outflows. And then there's weather-based ET simulations and then atmometer. I'm going to skip this slide real quick just so I can show that atmometer. These are made by ET Gauge. They're a company out of Loveland, actually, which is really cool. You fill up this cylinder with distilled water, and then it's got a straw inside of it. So it might be hard to see, but the water level right now is about at that 3. And then the top cone is a porous membrane, and there's different membranes you can buy to simulate your crop. And it will act as a plant would. And as that water evaporates through the top of the cone, this water level will go down, and you'll see the numbers are inverted. So you're actually reading water use. And so I really like these. It may not be super relevant for vegetables. You're not going to get a direct reading because a lot of these tops on these, the fabric cover on these is going to be made for fully irrigated grass or alfalfa or something like that. But if you know what the water use is on grass and you're growing onions or carrots, there are tables that you can use to say, okay, this is kind of my coefficient, and I can multiply that water use by what my actual crop is. So I like those. It's a cheap way and it's an easy way. It's basically just an inverse rain gauge. Okay, but when do I actually irrigate? I mentioned management allowed depletion earlier. That's typically going to be 50% of that available water capacity, but it depends on your availability of irrigation water, your system capacity, and your crop that you're growing, how sensitive that crop is. So for example, I didn't put it in here, but if you only have the ability to put on 1/2 inch of water per day, you can't get too far behind, because during the heat of the summer, you're limited to that 1/2 inch and you won't be able to keep up or potentially catch up from those hotter days. So you'll set your MAD based on a lot of different factors, but typically 50% is a good starting point on most of our commodity crops. More sensitive crops or higher value or shallow rooted, you're going to set that MAD a little bit lower so that you have a chance to catch up during the heat of the summer. So on this slide, that MAD was kind of set here, even though it's not labeled. Okay, what if I like a little bit of math? We can do this. We can set our MAD, so it's not very hard. 6.2 inches of water. I just pulled that table from up above. 50% MAD, multiply that 6.2 by 0.5. You now have 3.1 inches of soil water content to play with. Once you get down to using that 3.1, it's time to irrigate. If you're going to be a little bit more conservative based on those other factors that we talked about, and your MAD is set at 35%, now you only have 2.17 inches of water to play with. So that MAD does change things a lot, and it's influenced by all those other factors that we talked about. It's important to at least have that in the back of your mind. Maybe you're not going out to the 100th of an inch. That's okay. But it's still important to think about and keep that in mind of what is your system capacity on a year like this. If you're not going to be able to catch up during the heat of the summer, you might need to take that MAD down a little bit and have a little bit less wiggle room in your system. Okay. Get your graphing calculators out. Everybody brought those, right? Okay, maybe not. This is one of the equations for calculating ET. I just like to throw it in there. Here you go, Ian. So I put this in. I made this spreadsheet with the help when I was at CSU of one of Ian's close colleagues, and it just shows that ET per day is highly variable throughout the year. And we kind of already know that, but this is kind of what it looks like. So those averages on my previous slide are going to be that black line. But each day, you're going to have hotter, windier days. You're going to have cooler, cloudier days. But ultimately, you add all those up and you get your consumptive use. So this is also going to be highly dependent on location, wind, temperature, solar radiation, relative humidity, all those things. But you can find these tables on the Colorado, I forget. I'll send the link to Jess so that she can send them out. But for most metropolitan areas, they have these weather stations and they have the math kind of done for you. Granted, this is done on an average year, but you can see month by month what your typical consumptive use for typical crops is expected to be. Cool, right on time. So to kind of put it all together, these are some screenshots from the WISE irrigation scheduling tool that CSU put together. It's in their eRAMS platform. I'm going to pick on Ian for a second. Maybe you don't know. Do you know if they've updated this to the 3.0 version and if it's working again? And if you don't know, that's cool.
That I don't know. I think they did more funding to keep it around though.
Yeah.
WISE is part of that.
Cool. This tool shut down towards the end of last year. It didn't actually shut down. You can still go in here. But the data from the CoAgMet weather stations quit feeding into this because they're running some updates on that CoAgMet system that need to fit into WISE. So, but I just wanted to point out a few things here. So this is, if you look at the dates, we're in basically all of May, late April to early June. So we're at the beginning of the growing season here. On the left side, colorblind. So that top line, whatever color it is going to be your available water capacity. The middle line here is going to be your MAD. So I think this is set at 50%, but you want to keep that water between 50%. Does anybody know, or can anybody guess why those lines for available water capacity and MAD trend up when you hit May 20th in this case? Your rooting depth goes down. So now you have more soil to pull from, meaning the more soil your roots are hitting, the more available water you have. So you'll see early in the year, I'll go back to those slides later. Early in the year, you don't have a whole lot of wiggle room because your rooting depth might only be a few inches to a foot or so, foot and a half. And for full transparency, this is based on corn. But as that crop grows and you get through the vegetative development stages, your roots get deeper and deeper. Now your plant has access to more and more water. So this is the period right now through, whatever time it is for your crop, that it's going to be really important to not get below, preferably that MAD, but definitely not to permanent wilting point. So this is kind of a textbook example of what you want that to look like. You want that available water on this line to dip down towards your MAD. In theory, you'd have enough water to be able to put on 2.2 inches in this case, roughly, to get it back up close to field capacity. That's not always the case. In these cases where this line touches that line and we're still having rain, that's shown here. So our soil water deficit is 0, 0, 0, but we're still raining. So we're still putting water on in this year. We're not counting any water above field capacity because that's not part of your reservoir of your soil storage. As you get later on in the year, and this is just a quick example, within this WISE tool, if you have some other systems, maybe you have some soil moisture sensors, maybe you have one of those cool ET gauges or something like that, so all that stuff is automated based on weather stations. In this further right column, you can put in what your observed deficit is. So if you put in my deficit is 30% here, it will change the numbers from that point on to reflect your actual conditions that you've overridden the weather station on that date. So I really do like this tool. It's free, fairly easy to use. Just a couple more graphs real quick. I pulled this from Grow Guru. This was from a TAPS CSU research field last year. This shows a very similar thing, that available soil water is in the black, and then the green bar is supposed to show your available water content. So early in the year, that green bar is smaller. Later in the year, it grows a little bit to be able to show that the growth of that root zone. And then this cuts off in July 10th. So, it would probably stabilize at this point. And then, as you get closer to the end of the season and that crop is drying out, it'll go down a little bit. But so there are a lot of these different tools. Every company has a different way of visualizing this. One of the things I like to point out is don't pay too much attention to the numbers on the left, because every company is going to show their readings from their monitors a little bit differently. And, in this case, they're saying it's available moisture. Another company might put decimal numbers on there and might say 0.26. You're like, well, what does 0.26 mean? The important thing is really to look at those ups and downs and make sure you're in a range that you're comfortable with. This is from the same date range, or actually, I guess it cuts off 2 days earlier, but the same date range. This previous slide is all 12 of those sensors combined into one, and that may not be what you're wanting to look at. You might want to look at what is my soil water at 4 inches, 8 inches, 12 inches, something like that, so that you can manage the water within those zones that we talked about earlier. It's very messy. Not happy I'm colorblind when I look at a graph like this. I usually have to check them off and then click on one at a time, and I'm probably not getting the whole picture. But maybe you can a little bit better than I can. So, but these are really key to, if you do install sensors, and Ian will talk about those more later. If you have a deep sensor, it can be really helpful to know, are you putting on too much water? Are you getting that deep percolation? Is that water going beyond your root zone that you can't then tap into later? Now you're wasting water. So I like to toggle that lower one on first and make sure I'm not seeing any big spikes. If I'm seeing a big spike, I know that soil water content within that 4-inch zone, in this case, is high. And I can assume that the water below that is also having water intake, and my crop is not able to utilize that. So that was quick and dirty. I'm glad it worked out for the 45 minutes. I didn't run through this ahead of time, and it worked out perfectly.
5 minutes of
Yeah,
questions.
I also wanted to say there were some other questions earlier that I wanted to answer, but we got cut off, or not answer, but give my opinion. So if you want during a break, come find me, we can chat.
Questions?
What was the name of the sensor that you're using to measure the water, at those different depths?
This one was from Goat Guru, which actually they changed their name to Goanna Ag this year. I think it's an Australian company.
Okay.
I only picked from them because my team with NRCS is competing in the TAPS contest, and that's what we used last year. So
Okay.
I pulled those from our TAPS dashboard last year. But there are a ton of different sensors out there, and I'm not advocating for one or another. In our contest, we've changed sensors year over year just so we can see the different data that they're giving us. They are wildly different. Yeah. Some of them are really hard to read.
Does subsurface drip irrigation work well in clay, and at what depth would you choose for vegetable?
It can. Yeah, actually subsurface drip can work really well for clay because the clay particles will pull on that water real hard, right? And so if soil surface, your drip tape, let's say 6 inches, those clay particles will pull that water up so that you're able to germinate your crop. Where I've seen subsurface not work so well is on your sandier soils, because you can't pull that water up and it's really hard to irrigate up to germinate. So you're really relying on either a secondary irrigation system or natural precip to be able to germinate in spring on those sandier soils. Clay is pretty easy.
What's the best way to know that you have irrigated most? Is it just a sensor, or if you can't see it since you're using subsurface?
What do you mean? Sorry.
Just what's the best way to know?
So you can't see the water?
Yeah.
Yeah.
I mean, it was in one of your slides even. It was like, you might be overwatering, you might be underwatering because you can't see that the event really happened.
Yep. So first and foremost, especially we recommend flow meters on pretty much all the systems we assist with installing, but especially on a system like subsurface where you can't see that water, it's really key to know how much water is flowing through your pipes.
Sure.
Make sure it happened. And then unfortunately, if you're not out there poking holes and observing your crop, it's going to take a while, but eventually you'll see wet spots or dry spots if you have plugs. So you will see it, but by then it's probably too late if you have dry spots. But yeah, a little soil probe or something, go out every 100 feet or whatever and make sure your water capacity or the ease of which that soil probe goes in is about what you'd expect. And you can kind of assume that things are working pretty well. But yeah, it does take more than visual observation because everything's underground.
Some of those charts and calculations from earlier in your slides actually in that water book.
Like these. You want to do that? Yes. There is a table exactly like this. It's just a different soil that they use. Exactly like this in that book. Yep. Yeah, Owen.
You get a lot of requests each year from producers to come out and help them with this kind of stuff.
Not as much as I'd wish. Yeah. I enjoy doing this kind of stuff. This was recycled from a presentation I did like 10 years ago. I wish we did more. I wish we also had time to do more. So it's probably an okay thing that we don't get a lot of requests because time is shorter these days than it has been. But still, if we have the time, and we will try to make the time, we'd love to come out and help you walk through these on site specific cases. Yeah, that'd be so much fun.
We've got like a variable small acreage pasture, and I'm curious with that sensor, like it's obvious just looking at the field that it's not evenly irrigated.
Sure.
And so like how do you decide how many of those make sense and where to put them?
I'm gonna let Ian cover that in his presentation.
You can answer it if you want.
It's hard. I'm passing that off because it's hard. So the first thing I would do is go to Web Soil Survey or something like that and see what your soil types are. And that's not perfect because the scale of those soil surveys are 1 to 24,000, which is pretty big. So if you had a map on a piece of paper, you'd be seeing 3 or 4 miles across. That's the scale that these things are created at. So it's not super specific, but within those soil surveys, it'll give you a dominant component. So what we think that is, and it'll give you a percentage. 80% is probably going to be this soil. And then it'll give you minor components too. And Soil Web will do that as well. So you can say, well, what are the minor components in there Is that minor component sandier and that's what I'm observing? Well, then I'm gonna treat it as that minor component. So don't treat those soil maps as gospel. It's just what we think there is, but generally, if it's not that dominant component, it's gonna be covered by one of the minor components too. So look at that soils map. If you have 3 or 4 different soil types on there that are vastly different and looking at texture, it's probably worth putting more than one sensor of some sort out there. That's a good place to start. But then when you have an uneven irrigation system, that complicates things too.
But you're deciding first based on whether you think you have different soil types.
That's what I would look at first. Yeah, and not necessarily, you might have an alt band loam and then a Fort Collins loam. Well, at least look at the textures of those soils, and are they vastly different? And then look at that table that I just pulled up and look at your soils and see if that texture remains fairly consistent all the way down. They're not going to be exact. That alt band loam had a 13 to 24 inches or something like that of clay loam, I think it was. Maybe the soil next to it, or the minor component versus that dominant component, still going to have that clay loam band, but maybe it's a little bit bigger or smaller, and that'll define what series it is. But for irrigation purposes, I pay more attention to your textures.
Okay, so now we're gonna enter into our 10-minute break, and if you do have more questions, you can pull Will aside.
Yeah.
I was just gonna say too, if you have this drought strategies worksheet, you can start filling that out based on the presentations that we've had. And I'm gonna possibly look into doing a different irrigation. I'm gonna look into doing the scheduling. Maybe when Ian talks, I'm gonna look into getting these soil moisture probes. Those things that'll help you later on, or you can even fill it at home with your wife or husband or partner or whatnot, just to get on the same page about your drought plan this